Welcome to my presentation with the title SetSketch, filling the gap between MinHash and HyperLogLog. Sketching of sets is widely used in big data applications. It allows to summarize the elements of a data string or a data set using just few kilobytes and still allows to extract certain kind of properties of the original set. What we expect from such a sketch is that the aggregation should be idempotent and commutative. Adding the same element multiple times or changing the processing order should not have any impact. It should be mergeable to support distributed processing, and of course it should be as space efficient and as fast as possible. We consider the following use cases. First, we would like to be able to estimate the cardinality of the underlying set. Second, we are interested in estimating joint quantities like the Jaccard similarity or inclusion coefficients. And third, the same component of two different sketches should be equal with a probability that is a monotonic function of the Jaccard similarity. This is useful for similarity search, especially when using indexing techniques like locality sensitive hashing. Here's a brief comparison of some state-of-the-art sketches and the sketch we will present. MinHash is very good if you are interested in joint quantities or locality sensitivity. Unfortunately, aggregation is quite slow and it is also not very space efficient. HyperLogLog is mainly used for cardinality estimation. However, estimation of small cardinalities requires special handling and is susceptible to large errors, as we will show. It is not very suitable to estimate joint quantities as it does not contain as much joint information as MinHash. HyperMinHash is a recent development. It increases the register size of HyperLogLog to add more joint information. Its joint estimator is based on empirical observations and requires again special handling for small cardinalities. SetSketch, our new data structure, has a slower update speed for small cardinalities. However, in return, it comes with simple and robust estimation algorithms which work for all cardinalities equally well, and it can also be used for locality sensitive hashing. SetSketch defines the state as given here. This is very similar how HyperLogLog defines its state. However, the hash values are exponentially distributed and not uniformly. This definition implies a distribution that has a shape that does not depend on the cardinality. This is in contrast to HyperLogLog or HyperMinHash. The location of this distribution depends logarithmically on the cardinality. Due to this scale invariance, the estimators we will present will work well on any cardinality range. The distribution has an unbounded domain, but it is highly concentrated such that only a limited number of values are possible with a reasonable probability. For example, when using these values for the base and the rate parameter, 2 byte registers will be sufficient to represent sets up to cardinalities of 10 to the power of 18. The naive implementation would lead to an incremental update time that scales with the number of registers, because for every element and every register, a hash value and the corresponding update value needs to be computed. The component-wise maximum defines the final state. To speed up the computation of SetSketch, we keep track of some lower bound of all current register values. Furthermore, we calculate the hash values in ascending order such that the register update values are descending according to this formula. This allows to stop the process as soon as the update value is smaller than or equal to the tracked lower bound, as further update values won't be able to change the state. Since the lower bound increases with the number of distinct elements, we will often be able to stop right after calculating the first update value, which finally results in an asymptotic constant update time for large cardinalities. How can we calculate the hash values in ascending order? The idea is to generate an ascending random sequence of values and use them randomly as one of the hash values using shuffling. The random sequence must be chosen such that the hash values calculated in this way are again exponentially distributed. For that, we propose two different techniques which result in two flavors of SetSketch. The first approach sums up exponentially distributed spacings, which will result in statistically independent hash values. The second approach partitions the probability density function of the exponential distribution into equally sized areas, and exactly one sample will be taken from each of those partitions. In contrast to the first approach, the hash values will be correlated. However, our experiments have shown that the same estimation algorithms can be used as for SetSketch 1, and they even give more accurate estimates in case of small cardinalities. The experimental results confirm the asymptotic constant recording time for large cardinalities. SetSketch is significantly faster than MinHash, as you can see here, but it is slower than HyperLogLog for small cardinalities. However, in return, estimation will be easier and more accurate, as we will show in the following. We were able to derive a closed-form cardinality estimator that works for all cardinality ranges. SetSketch 1 shows a constant estimation error that matches the theory. SetSketch 2 even reduces the error for small cardinalities, like HyperLogLog. However, when analyzing the kurtosis of the estimation errors, we see values for HyperLogLog that are much larger than 3, which would be the expected value for a normal distribution. This indicates a high probability of estimation outliers for HyperLogLog. To solve the joint estimation problem, 3 unknowns have to be estimated: the cardinalities of both sets and the overlap. If a sketch is mergeable, the inclusion-exclusion principle can be used to estimate the intersection size and also other joint quantities. However, this approach does not use all the joint information that is stored in the sketch. For SetSketch, we were able to find these simple expressions, which are very accurate approximations of the probabilities that a component in one sketch is greater, smaller, or equal compared to the same component in the second sketch. After finding the cardinalities using the estimator presented before, we can simply use the maximum likelihood method to estimate the Jaccard similarity. Since the resulting log likelihood function is very cheap to evaluate and strictly concave, the maximum can be found after a few iterations using standard optimization algorithms. Here you see the root mean square error, which we obtained when estimating different joint quantities. Since the estimation is scale invariant, we fixed the union cardinality here, but we varied the Jaccard similarity here and also the ratio of different sizes on the x-axis. In all scenarios, the new estimator performed better than the inclusion-exclusion principle. It can also be seen that smaller base values may reduce the estimation errors significantly, especially if the sets have small overlap, like in this case. We have shown that SetSketch with base close to 1 is similar to MinHash. For this special case, it turned out that the maximum likelihood estimator can be explicitly expressed, like shown here, and outperforms the original MinHash estimator, which was not optimal, as it even performed worse than the inclusion-exclusion principle in some cases, as you can see here. The new estimator can also be applied to HyperLogLog because its state approximates that of SetSketch with a base value of 2 and a rate parameter equal to the inverse of the number of registers. It gives better results than the inclusion-exclusion principle. Our joint estimator also performs better than the original estimator when applied to HyperMinHash and does not rely on empirically found magic constants. The expression that we have found for the collision probability has only a weak dependence on the cardinality. The figures show possible values of the collision probability over the Jaccard similarity for different base values. In particular, the last chart shows that SetSketch is well suited for locality sensitive hashing. Since 2 byte registers are sufficient in this case, the space may be reduced by more than 50% compared to MinHash, which usually requires 4 or 8 bytes per component. We have presented a new data structure for sketching sets. It comes with simple and robust estimators for cardinality and joint quantities. And as a byproduct, the joint estimator can be applied to improve estimation from HyperLogLog, MinHash, and HyperMinHash sketches. And finally, the locality sensitivity of SetSketch allows its application for similarity search. Thank you for listening.